And one is that the planet revolves around the sun with the sun at one focus. This picture you recognize from yesterday, except that I have the Earth where it would be at the perihelion or the aphelion, and the astronauts tell us the Earth looks blue, so I've made it blue. And like all the preschoolers and pre-K and kindergarten people, I have to put the sun in the picture, right? If you have any experience with little kids, they always do that when they're 4 or something like that. So I'm lucky if I have the mind left of a 4-year-old, so making my picture with the sun. Anyway, the sun at one focus, and the orbit then for the planets is some kind of ellipse. Ours is nearly circular. It has an eccentricity approximately 0.17. If it were 0, you see, it would be a perfect circle. It would be 0 out of round. That was the original idea of eccentricity, that it was measuring out of roundness. And anyway, the radius vector would be a line like focus to where the planet is, would be like the R here. Connecting the sun and the planet sweeps out equal areas in equal times. So what that means, you see, is that when it's closer, when it's over here compared to when it's over there, what you have to do to get an equal area over here compared to what it would be when it's over here with a much longer radius is you have to go faster so that you cover more arc. You need, if it's to be equal area, and if it's a shorter radius, you need a longer arc. And if it's a longer radius, you do a shorter arc. So we actually speed up and slow down during the year, but we don't realize it. And so that's the second Kepler law. And then the third is the square of the period of revolution is proportional to the cube of the length of the major axis. So they apply to an object that's orbiting one much larger object, so that the force field is essentially all the gravitational force between the larger object and the smaller one. If you have other parts of space where you'd have competing gravitational fields from several stars or something like that, then these laws would not necessarily be it, because you'd have a more complicated situation with other forces getting into it. And so you, without being specific about just what the other forces are, you can't say much. So then Newton added to this, but this was the basis on which Newton worked. If the orbit's a conic section, parabola, radius, hyperbola, so on, with eccentricity E, so here is what we got yesterday, if you recall. Then the gravitational force is proportional to 1 over the squared distance between the center of, thinking again of a sun and single Earth system. The distance d would be the distance between the center here of the Earth and the center of the sun. So it's 1 over this distance squared, not 1 over the square root or the cube or something else. So this was really a big thing to prove that it's a 1 over the squared distance type law as opposed to something else. And this is actually one of the real triumphs of calculus. What you have to do to prove this is, first of all, you have to be able to put the equation for the path, which we call our ellipse, say our conic section, in polar coordinates. And that's one of the main reasons for all of this section 11.7 we've been talking about, is to get the conic in polar coordinates. And then if you assume that the force is a center-to-center type force, you can prove that it's 1 over the squared distance. And you can also prove, as Newton did, that if the only force that's acting center-to-center, which you call a central force in physics, and if it's 1 over the squared, 1 over the r square type, where r is the distance, then you can prove the orbit has to be a conic section. So it's if and only if, conic section orbit and 1 over the squared distance. And the key to being able to do this actually is getting the polar coordinate representation of your conic, because as we've seen, it's the same representation no matter what it is, parabola, ellipse, hyperbola. The difference is what's the e value. 1, remember, for parabola, and less than 1 for ellipse, and 0 actually for circle, and then greater than 1 for hyperbola. But the mechanics, in the sense of the gravitational type force being 1 over the squared distance, the mechanics are the same for any of the conic sections. And for the 1 over squared distance type mechanics, the path has to be a conic section of some sort. So, if you think of the Earth, where our conic, if you've written it this way, which we saw yesterday you could do, what the numerator here replaces the EK, then for the Earth, the eccentricity is approximately this number according to your book. And they also tell you in the book that 2A, which would be your major axis length there to there, is approximately 3 times 10 to the 8th kilometers. So the A is half that, which is this number. And then the R, if you put this value in for the A and this value in for the E, and put the E value in here, would be like this. So as we said yesterday, you have the perihelion when the theta is 0, and so then you're dividing by 1 plus the E, and if you take 1 plus E here and cancel, you notice this factors as we did yesterday. This is 1 minus E times 1 plus E. You cancel the 1 plus E and it leaves you the A times 1 minus E. And if you take this A value and this E value, you get this many kilometers. And if you're at aphelion over here, where the angle is pi, your cosine's -1, so then you're dividing by 1 minus e and canceling the 1 minus e factor, so it leaves you a times 1 plus e, and that works out to be this. So the difference between this far and that far for us is approximately 5 million kilometers. And as I said yesterday, that's a long way to walk. Our orbit is much more circular than in this picture, certainly. But even though it's much more circular, it isn't exactly. There is a significant difference, and we see it in the weather patterns and things like that. How much daylight we have in the summer, and so on and so forth. So it is noticeable to us. This we went through yesterday. This was in the process of getting the derivation of this form of the conic section as opposed to this one. In other words, you can replace the EK with the A 1 minus E squared, because as we said yesterday, K is the distance from your focal point over to your directrix, and measured from the center, we saw that the distance x is A over E, or A squared over C. So K is this minus the distance from the center here into the focal point, and so that is the C, which is EA, and so then you do some algebra here, and this is what you get. So that E times K then, multiplied by E there and there, is A times 1 minus E squared. So for work with astronomy, you tend to work with the eccentricity and the A value, and not really with the directrix itself. Okay, now let's look at some problems that are in the 11.6. Number 70 is interesting. They are telling you that if you imagine a suspension bridge cable that's supporting a uniform load of W pounds per horizontal foot, then for horizontal tension H at the origin, the curve will satisfy this differential equation. So the problem 70 is giving you this. The derivative then, where y of x will be the elastic curve into which you would bend the bridge cables in order to have minimum tension, horizontal tension at the origin, that the elastic curve is the solution of this differential equation. Derivative is your load per foot over your horizontal tension times x. And your initial point would be where the cable would be down at the origin, so x is 0, y is 0. So you separate variables and you integrate both sides. And so you integrate here and you have x squared over 2 plus constant. So then you can get your constant because you're saying y is 0 at x equals 0. So your constant 0. So the elastic curve for minimum horizontal tension with a given load per foot that's, say, W, is a parabola where the coefficient is the W over twice the horizontal tension. So that tells you then that to get minimum tension in the bridge, you would deform the cables into a parabolic shape. And if you're thinking of an arch supporting a roadway, your arch would be parabolic in shape. If you remember the first day last week when we were talking about conic sections, I had a picture from the Braid magazine of the arch that was parabolic. So look at problem 57 in 11.6. So we have this conic section, and this is what you would call the general form, where you have possibly x squared and something times x and y squared and something times y, and also possibly a term with a number times xy. That would be if your axes of symmetry of your conic section were at an angle relative to the x-axis and y-axis. We haven't talked about that sort of thing because your book doesn't go there, but it is possible to go there. And this one is in fact a circle because you have equal coefficients on the two squared terms. So to determine the location of the center of the circle and to determine the radius, you complete the square, as it's called. And then the coordinates HK will be the coordinates of the center, and then you can find what the radius is. It'll be the square root of whatever ends up on the right-hand side as a single number. They're supposed to teach completing the square in a class, well, second year algebra in high school, or a class like Math 108, or certainly by 143. However, that doesn't mean that they have or that you necessarily remember about it, so I'm going to do some of these. So what you do when you have a square in a letter and a first power term in a letter, to complete the square, as it's called, if your coefficient on the square is a 1, then what you want to add to both sides is half of the coefficient of the first power letter squared. So this is a 1, so I just take this, 4, half of it, so I'm dividing by 2, and square. And of course, if you add on the left, you have to add on the right, because we keep honest books in the math department, right? And so 4 over 2 is 2, squared is 4, so I just wrote it as 4 over here. What I'm adding then is 4 on both sides. Then, if you do this, the three terms, the square that had a coefficient of 1, the first power, and what you add, will be a perfect square. It'll be whatever is the letter, plus if this is plus, and minus if this is minus, the number that's here, the 2, the whole thing is square. And you can see it works. If you square this out, you get x squared, 2x twice, and then 2 squared, which is there. With here, there is no first power of y, so you don't do this here. It's just y minus 0, if you want to say it that way, square. And then 12 and 4 are 16, and so that's 4 squared. So the center of your circle, you set this equal to 0 and solve for the x value, so that's minus 2. set this equal to 0 and solve for y, so that's 0. And then the square root over here is your radius. And in the directions on these problems, they say get foci and eccentricity and asymptotes, but that doesn't really apply if you have a circle. You don't really, well, you have one focus point, which is the center, but usually you don't bother to say it. And you don't have asymptotes. And the eccentricity for a circle is 0, because you don't really have the C there. So it's just defined as 0. So then look at problem 63 next. We have x squared minus 2x, and we're going to add something, plus 2y squared minus 4y, and we're going to add something else here. And we have minus 1, and we'll have to add over here, consistent with what we've added there and there, of course. And you notice that these coefficients on the square term are different, so it's not a circle. They are, however, both plus, and so when they're both like sign, then it's going to end up being an ellipse of some sort. If your coefficients on the square terms are opposite sign, you're going to end up with a hyperbola like over further. So again, this coefficient is a 1, so what I'm going to add here is half of this coefficient squared, which you see would be minus 2 over 2 squared. So I'm really going to add a 1 there, and I'm going to add a 1 there for it. Then with this one, when your coefficient on the square is something else besides plus 1, what you want to do is factor whatever this is from your square term and your first power term. So I factor the 2. So then inside the brackets, I have y squared, and then here minus 2y. See, I factored it out of all of y terms. And whatever I do here, 2 times it is what I'll be doing over there. So this actually, that number is actually wrong. And so I take half of this, which is actually minus 1 squared. So I'll add 1 there, but I have this 2 out here, so it's this 2 times that 1 that's really going over there, because the books have to balance. So this can be a 1, but this 2 times it is this 2. See, I go through that on this line. This 2 is here, and then I use the red to point out this times this is what's there. And that's what I have there. So what I have now is 3 terms here plus 2 times 3 terms here equals 2 on the right, because those 2 cancel. And you see, this is x minus 1 quantity square, and this is 2 times. With these 3, you can see it's y minus 1 square equals 2. So to go to what we call standard form, you always want a 1 over here. So you divide by it. You divide by whatever's here, which is the 2, which is square root of 2 squared. So that'll be the denominator here, and then when you divide by 2, it'll cancel this one, so your denominator here will be 1 squared, and then you have 1. Okay, the plus tells you it's ellipse. The larger denominator is the a, so that's the square root of whatever this denominator would have been, which is root 2, which is larger than the b, which is 1. So the a is root 2, and the b is 1, and the center then is at 1 and 1. You don't have asymptotes, and if it's an ellipse, you don't have a radius. The radius went back here with the circle. But you do have a c for the ellipse at a squared minus b squared, so c is 1. The eccentricity is c over a, so it's 1 over root 2, which is less than 1, which is ellipse, you remember. And your major axis is horizontal because the major axis is parallel to the letter named axis, x or y, that has the biggest denominator. That's a mouthful to say it, but that's what the rule really is. So the long way is parallel to the x-axis. And the vertices then and foci will be on a horizontal line that goes through the center, the line y equal 1. So the vertices then are the x-coordinate of the center, which is 1, plus or minus the a value, root 2, and then the y-coordinate would be 1, and then the foci in the same way, starting from the center, 1, 1, you're going to go c to the left and right, so 1 minus 1 is 0, and then 1 plus 1 is 2. So you see, you can take something that's given in the general form like this with squares and first powers and numbers, and you can sort it out that it's an ellipse, and then you can draw the ellipse when you get its center and this other information. This is all stuff that supposedly is taught some of in Math 143 or 147, and maybe you got some of it and maybe you didn't, but I'm presenting the class more or less as if you didn't, let's say, and if you know all of this code, then I apologize to you, but I think not everybody does, really. So let's go on and talk about hyperbolas over there. If you were here yesterday, you recognize that these pictures were left over from yesterday. We might look at this just a minute before we go over there. I guess I'd better do. As you know, if you were here yesterday and Friday of last week, when we started talking about conic sections in polar coordinates, the setup that you use to get them represented in polar coordinates is you think of the center of your conic, and then you have a focus where your curve would be bending over the focus. So if it's this picture, then if it's hyperbola, you're thinking about this branch of the hyperbola for this model of focus, and then curve, and then directrix as you go left to right. And if it's ellipse or parabola, you're thinking of your focus here, and curve and directrix, or parabola, focus, curve, and directrix. And then the directrix is over here. So then the R, you take your origin and your pole here at this focus. So R is the distance to any point P on the curve, and then you have a straight line coming in at right angles here, distance from this point to D on the directrix. And so we define for working with polar coordinates our eccentricity as the ratio of this distance to that one. And we spent quite a lot of time yesterday showing that if you've defined your eccentricity this way, EFP over PD, and if you also believe that the distance from the center of your conic to the directrix X is A over E, then you conclude that the eccentricity has to be C over A, which is what we use in problems like these. If you were here yesterday, you remember we went through it in considerable detail here, that you have three statements about eccentricity. C over A, the ratio of this length to that one, and then that from here to the directrix is A over E. You can take any two statements and prove the third one from it. We did it all three ways. It's right here yesterday, if you remember. So, as you see, if you take your eccentricity as this distance over that, this is R, and if K is the distance from your focus to your directrix, then that minus R cosine theta down here in the red gives you the brown distance, which is the length here, the K minus R cosine theta, which is up here too. Okay, so then you have E is this over that, and then if you multiply denominator here by E, you get this R equals this E times this K minus the E times R times cosine theta. Then if you move this term across and solve for R, you get the polar coordinate formula for your ellipse. If you take this line and solve, you see what you get is R first you get that, and then you factor the R and solve. Well, it's EK. So you do just that much algebra, and you can solve for R, and then that's your form in polar coordinates. points. And we spent quite a bit of time looking at Maple yesterday, seeing that something like this will graph to be an ellipse or a parabola for all of the problems that were in the section 11.7. And as I was saying earlier today, you have to get your conic in polar form if you want to do as Newton did and prove that your gravitational force is 1 over the squared distance between the centers of your sun and your earth, for example. So this is one reason it's so important. The other thing is that you can do as we talked about here yesterday and replace the EK in the numerator here with the semi-major axis length and the eccentricity. So you can rewrite, you can go from here now and get to there by going through the thinking that's right here, which is what you do in astronomy. Okay, so now let's finish for the week and for the chapter with a couple more of these complete the square game type problems. These two are hyperbolas. So problem 67, you're given this. And the fact that you have opposite signs here is your clue that you have a hyperbola. And so again, you want to complete the square because you see you have a first power of the y. So you have no x first power, so you leave that alone. With this, your coefficient on the square is -1, not 1. And what I was saying to you here still applies. If your coefficient on your square term, where you're going to complete the square, is anything except +1, factor out whatever it is. So factor the minus sign on the terms involving y. So I have the minus, so now that's +y squared, and that changes from plus to minus there, so I have 6y. So then what I'm going to add here is half of this coefficient square, so that's -3 squared. So in other words, I'm adding a 9 here, but it's inside of parentheses. So really this minus applies to this 9. I put 9 there, but I have minus time 1 times it, so it's really -9 goes over here, matching what you had here to what you really did here, which is minus this 9. Okay, now you can always say, if this is what you've added here, that you have the square of whatever this is, minus if this is a minus, plus if this is a plus, the number here that's the square root of what you put here. So you have y -3 quantity squared gives you this, that, and 9. So you have 2x squared minus this quantity square is the original 3 minus 9, this minus times that 9, which is -6. And that's all right, because when you go to standard form, you divide by whatever this is, minus and all, if it's minus. So I divide by -6, and then I have a +1 over here. And now you see this will be the term with the plus. So you might have started out thinking the x was what had the plus, and it was going to be a hyperbola this way, but it isn't, because when you get to standard form, the plus is with the y. So the transverse axis is vertical and not horizontal. See, these things can fool you. And so 2 into 6 is 3, and so which is over here, so I have this over 6, which is square root of 6 square, minus then, from here, the x square over square root of 3 square is 1. So this is the a. The a is what goes with the plus sign when you're in standard form, and the b is what goes with the minus sign when you're in standard form. And the c square is a square plus b squared, so it's 9, so c is 3. So your transverse axis is vertical, as you see in the picture. Your center then is at 0 and 3, because the center is at hk, where h is 0 and the k is 3. So that's there. Your x-axis is down here. Then your vertices measured from the center, if you, of course my hyperbola here goes the other way, but measured from the center to the vertices is A, and to the focal points is C, and then the B does not really intersect the curve, but it's a construction that you use to get the slopes of the asymptotes, construction distance, say. So you're going from the center, the A, which is root 6, either up or down. So here's your center, and then this would be your root 6. And that's a number between 2.4 and 2.5 if you figure it out. So counting here, I go 1, 2, and a little more, you see, up to the vertex, and then down the same way, 1, 2, and some more. And that's not perfectly drawn, of course, but it's the idea. And the focal points then go from the center, as you see, like this, the C value, which is 3, so this one is clear down here, because this was at point 3, and this one would be up here at 6. So 0, 0, and 0, 6. And then for the slope of the asymptotes, you see when your transverse axis is vertical, then the slope here, your rise would be the A and your run would be the B. So it's A over B, plus or minus. So root 6 over root 3, which is root 2. So the asymptotes are lines through 0, 3. This has slope root 2, and this is slope minus root 2. So you do your equations of the line when you know the slope and you know a point, and so you get this. And finally, the eccentricity is C over A when you're doing things in XY form, so that's 3 over root 6, which is greater than 1. Your root 6 again is between 2, 4 and 2, 5, so your numerator is bigger. which it ought to be for an hyperbola. Okay, last one, number 68. Again, you have a square term and a first power term, so you have to complete the square. I've chosen examples here where you have to complete the square, so I could go over this with you, because it's something that people don't get very easily, I have found anyway. If all of you feel that I'm wasting your time and insulting your intelligence, I apologize, but I'm hoping that somebody thinks it's worthwhile. Okay, so I take these, and you notice there's a minus as well as the 4. So I have to factor that from the x terms. So over here I have the minus 4, I have x squared. So then 16 divided by minus 4 gives me the other minus 4 here to put with the x. Okay, so working with what's inside the parentheses, when the coefficient is 1 on the square term, then on the first power term, take half the coefficient and square, and whatever that number is, these 3 in here in the parentheses, which are in this case x squared minus 4x plus 4, will be a perfect square. They will be the letter, the x, minus if this is minus, plus if this is plus, the square root over here, quantity squared. You can multiply that out and you'll see it'll give you those 3 terms. And then the y squared, you can say it's y minus 0 if you want, or not. And you started with 24 here, and what you've really done, you see, you have a 4 there times this minus 4, so you're really adding a minus 16 on the left, so you have to do that on the right. So it's minus 16 and not 16, because there's a minus, and when you squared this, you'd have had a plus 4. So 24 minus 16 is 8, and you can rewrite this as your square. Then standard form, divide by the 8, and you notice the term with the plus is over here, so put it first. Then the minus 4 over 8 is the 2 under the x minus 2 square equals 1. Okay, now you can read your center. H is 2, K is 0. Your A is square root of the denominator of the term with the plus sign, so root 8. Your B is square root of the denominator of the term with the minus sign, so it's root 2. And C squared is the sum of these squares, so it's 10. And so C is root 10. Eccentricity C over A is root 10 over root 8, which is greater than 1, which it should be. And you see my picture here. My origin is back over here. My center is 2 over, 1, 2, and 0 up. And the asymptotes cross there. And then my vertices are at the 2 over, and then the A, which is the root 8, up and down. So 0, 0 plus the root 8 would be the y coordinate there, which is √8, so 2 over and √8, and then 2 over and minus √8. In the same way for the focal points, you're starting here and going up and down by √10, so 2 √10 and 2 minus √10. And then your asymptotes, again, when it's long way vertical, the slope is A over B. Remember, if it's turned the other way, the slope is B over A. So your A over B, let's see, square root of 8 over square root of 2 gives you square root of 4, which is 2. So your slope then is 2, or minus 2 for this one. And you take the coordinates of the point on the line, which is your 0, 2. So y minus, or it's 2, 0, pardon me. Y minus the y coordinate is y minus 0, slope x minus the x coordinate, which is 2. And then do it with the other slope, and you get these two lines. Here's the picture. Well, what we will do the rest of the semester is Chapter 10, the sequences and series. The take-home part of the final is all Chapter 10 stuff, and part of Test 4, which you haven't received yet, is Chapter 10 stuff. So I give out Test 4 when we've gone far enough in Chapter 10 so you can do the Chapter 10 problems that are on it. The final is, in class, is the comprehensive part of it, so it's partly Chapter 10, and one of the things that's on the final is related to this stuff, and you have to know the definition of eccentricity, so that's why I've been beating you over the head. You have to know that E equals C over A to do one of their questions. So anyway, I think everybody knows that we do not meet next week, so I wish you a happy vacation if you're going anywhere. Vacation from me, anyway. Okay. So I'll